And I think we should be live. Testing, testing. If anyone is already here or as you join in, say hello in the chat. So I'll post in there real quick myself. And then also, if you want to let me know in the chat that you can hear me, that would be great. I normally have a better kind of audio setup going on at home, but I'm actually traveling, so I'm doing this from a hotel. I think the internet seems like it's good. And again, hopefully my audio is okay, but if you want to let me know in the chat, just for me to confirm, that'd be great. And we'll get going here in a minute, or maybe a couple minutes. We're going to wait for people to join in, and then I'm going to go through some slides. Hopefully they'll be pretty quick. I'm going to try to go through them super quick, and then we'll go into code and actually build a computer vision pipeline and object detection model and fine tune it on our own data. And I'll go more in depth into that a little bit later. But we're going to be building basically a production grade MLOps or computer vision pipeline here. And then we'll end up with a couple forms of how we can use our model. So we'll have a model that's trained on our own data set. You could go after this workshop, label your own data set, bring it into the pipeline, and then come away with a trained model that's doing object detection like here, but it could be on, again, any object you want to do. I think it's really fun. Like a lot of people have images of their pets that they, after this workshop, go label those and train a computer vision model on that. There's also definitely other labeled data sets that you could go ahead and take if you didn't want to label your own too. So again, we'll get going here in a couple minutes. Just waiting for people to join in. I think I even started a minute earlier than I thought. So it's exactly 12 now. And I know people usually roll in, obviously, a few minutes later. So again, say hello in the chat. And if you want to share a little bit about where you're watching from, I think that's always fun. And then maybe a little bit about why you're interested in computer vision or building AI pipelines. I always love hearing like what people are building as well, or why they're learning new skills. So I see some people rolling in. Again, we'll give it another minute or so. And like I mentioned, we'll go through some slides, and then we'll go through a lot of code. I'll probably share these one more time before we really get going here. But if you're like me and you want to go ahead and poke around at the code, you can go to that link. And that's going to be the code that we're running. And then also you'll need a Union account, which you can sign up for free here. There's no card or anything required. All you need is a GitHub account. And then it can take 3 to 5 minutes for the sign up to go through. So if you want to go ahead and do that for the setup, that's great. And let me just make sure while we're waiting here, I'm just going to make sure that I am live in all the right places, that my audio is working. And just give me 1 minute to do that. And also say hello in the chat. So I see more people joining in. Hello, hello. All right, cool. All right, I'll give it 1 more minute and then we'll start rolling if that works for everyone. Oh, no one said hello in the chat yet. It's fine if it's quiet, but it's way more fun. Awesome. Someone said hello there. Thank you. Thank you. And I checked my audio. It sounded like my audio is coming through, but again, let me know if it sounds weird. Again, I'm in a hotel today, traveling. Let me pull up this event. So if you happen to be in San Francisco, I am talking at an event later today. It's going to be on building AI agents and like agent orchestration. So if you happen to be in the area and you want to check that out, it should be pretty fun. And if you have any recommendations in San Francisco, I always love hearing them as well. With that, all right, I see people rolling in. I'm sure some people will roll in later. I'll share these links one more time because I did see a chunk of people just come in. So I'm going to go through slides. Hopefully it's going to be pretty quick for me to go through the slides, but let me know if you have any questions as we go. I'm trying to kind of read the chat as I'm going to be presenting, and then definitely as we're going through all the code. This is the link to the code if you want to go ahead and start poking around at it. That brings you to a GitHub. Most likely you're going to want to run this in a Collab Notebook. You could do local setup, but it's designed to be able to easily run in a Collab Notebook during the workshop so that you don't actually have to do any local setup, because that just causes other errors sometimes. So we're actually going to run all this in a Collab Notebook when we go to this hands-on portion. So like I mentioned, I'm going to go through slides first, and then I'll come back and walk through all this code. But if you want to go ahead and start running the code and looking at it, you're more than welcome to. And then, like I mentioned, for this, you're going to need a Union account. We'll talk more about what this is later, but it's going to be the platform that we're going to run our training pipeline on. And it has a lot of cool built-in features that you would want in your production grade pipeline. But this also gives us like GPU access. So when we train our model, we'll be able to use a GPU from there. And again, it's free to sign up. There's no card required. You get like $30 of cloud credit, including the GPU runtime. So we're going to be using that. And then just one more link that I'll share right at the beginning here. This is an event also next week on Tuesday. We're actually going to be talking about Flyte and Union version 2. Again, I'll talk more about those later, but Flyte is the open source project that Union is built on, that platform I just mentioned. So most of what we're going to see today, you can also implement in the open source. And I'll link to all that a little bit here as we go. So I'm going to go ahead and start the slideshow. I saw a chunk of people join in. Links to follow along and everything should also be in the description, but I just shared everything in the chat. And then if you have questions, put them in the chat. And also, since a lot more people just joined, say hello and maybe where you're watching from and why you're interested in computer vision pipelines, or if you have any project ideas that you're excited to build. It's always fun to hear in the chat. Just a tiny bit about me. My name is Sage Elliott. I work at Union. Again, that's a platform we'll see here. Also, just as we go through this workshop, even if you end up not using Union or Flyte, I hope you're going to take away some interesting concepts, both around computer vision. So we're actually going to, again, train a model. So we'll actually see this kind of computer vision side and model training side. We'll also see that building MLOps pipeline side. So if you've done one or the other, hopefully you'll learn something from the other one. Or if you've never done both, you'll actually see hopefully some cool stuff in terms of like building production grade pipelines for machine learning or AI applications. So I live in Seattle, but as I mentioned, if you're at the beginning of the stream, I'm actually in San Francisco today. That's why I'm in this hotel. I don't have my good audio mic. Again, it sounds like everything's fine though. And I think the hotel Wi-Fi is actually really good. So let me know if there's any issues, but it seems like it's going pretty good. And I also run an AI book club. So if you're interested in reading a new AI book every month, we've been doing that for a year and a half. And currently we're reading Reinforcement Learning for Finance, which we're going to discuss next week. But then after that, we're going to read, I forget the exact title. I think it's called Building Agentic Systems or something like that, but it's on agents. I'm excited to dive deeper into that. And if you want to stay connected and hear more about those events, follow me on LinkedIn. But you can also join our community Slack channel where we talk about machine learning and kind of all these other events and stuff going on. And previously, I've done a lot of work in computer vision, ML monitoring and evaluation, MLOps in general. And then previously, I also did a lot with hardware, IoT, and a little bit of robotics. And I still love to like fiddle and build robotic stuff for hobby things. What is object detection? So some of you might already know. You've probably seen at least some form of this demoed somewhere. But this object detection is a type of computer vision model or application where not only does it classify what's in an image, like you've maybe seen demos of saying like a cat or dog classifier, but object detection actually detects and classifies usually multiple objects, or it can do multiple objects in an image or video by drawing these bounding boxes around them and then assigning a label. So it's classifying that this, in this case, this is like a Flyte sticker and that's a Union sticker. It's classifying what class it is, but also drawing approximately where it is with these bounding boxes. And this really allows you to do more powerful things with computer vision than just the classification. So like even just for this, now you could count how many are in the frame. You can combine this with other algorithms like object tracking. So you can actually see how many of these things move across the frame and do counting. You can see interaction between the bounding boxes. You might have seen examples of like self-driving cars and use object detection to locate like where people are or bikes are with their computer vision systems. So object detection really allows you to use really powerful things with computer vision and is a really cool kind of step up from just doing like a classification project if you've done that before. To build your own, so there's like pre-trained models. We're going to take a pre-trained model and then fine-tune it on our own data set. I'm not going to make you label the data set. That can take a while and sometimes can be annoying, but there's a lot of really great tools now that have auto labeling capabilities. You should check out like Voxel 51, some of these other labeling platforms where you can bring in like visual language modeling now. They can help you get started with it. I use Label Studio, but you could also check out CVAT, Labelbox. Again, there's a whole bunch of them. But you could build your own label data set. So if you like this workshop and you run all the code, but then you want to bring in your own data set and run object detection on your own data, you could do that with like using one of these tools. And basically what you're doing is labeling the data with bounding boxes, kind of like we saw the model predicts. You do this a whole bunch of times for your data set. You want to have a good variation. For production, you usually have like a ton of images, but if you're just starting out for hobby stuff, I don't know, my rule of thumb is like try to get 50 to 100, train the model, see how well it does, and then you're probably going to want to collect more variations. Having more variations of like lighting or positions of those objects will help your model work a lot better. You want to make sure that you're labeling them properly. So you want the bounding box to be as tight around the object as possible, not in it or not well outside of it. If one appears in your data set and you don't label it, that's going to throw out the model while it's learning. And then you usually want to split these data sets into training, validation, and test. And we'll talk more about that when we get to the code. And today we're going to use a faster RCNN model, which is a two-stage model. There's different types of object detection models. This uses a backbone, by default ResNet, but actually today we're going to use a MobileNet, which is a smaller neural network, and actually allow us to run it on like CPUs. And in fact, you could take the model that we're going to train today and run it on like a Raspberry Pi and get a decent frame rate, like 4 or 5 frames per second, which is actually pretty good for just like no crazy optimization, running it on a Raspberry Pi. And then you could use that to do like your home security or a robot or something like that. And kind of at a high level, how the faster RCNN works is it has a region proposal network. It's actually going to kind of use the classifier that's trained and say, well, I think the object I was trained on is around in these boxes. And then it does bounding box coordination within that region proposal and then tries to figure out this is actually the best fitting box of like between all those region proposals where the actual object is. And faster RCNNs usually have pretty high accuracy, but sometimes they're a little bit slower than single stage object detection models. Like you probably heard of maybe YOLO models. There's another one, single shot multi-box detection, which works pretty good. So if you want more optimization, smaller models, you can use one of those, but sometimes the accuracy is a little bit less, but they're all kind of catching up on each other. So you can try the latest versions and see what's going to work best for your use case. And then just to touch on kind of the pipeline. So again, like I mentioned, this actually isn't the right bit.ly. That's from a different workshop that'll take you to fine-tuning an LM. Like I mentioned, we're going to train our model, but we're also going to build like a production grade pipeline and use MLOps, like the set of best practices of combining those practices and tools to deploy, monitor, and maintain your machine learning models in production. And then I like to think of the terms of reliably and efficiently. You might hear like durability, other terms that kind of mean the same thing here. Typically, you're going to have at the bare minimum some sort of pipeline that looks something like this. And again, let me know in the chat if you've built something like this before. It's kind of fun to hear about people's experiences. You're going to collect data. Usually, you're going to do some other stuff with that data, like we mentioned, annotation or pre-processing. Then you're going to train a model on that data. You're going to evaluate that model, make sure that it's working as good as you think it should be before you ship it into production. And shipping in production really, really means different things, because like you could be putting this in the cloud, you could be putting this, like we mentioned, on a Raspberry Pi that could be in like a literal field looking at plants or something like that. So a lot can go into this, and then depending on how you ship it, monitoring is something you want to do in some way. Again, it depends on how this model is kind of deployed, but you want to be monitoring over time and ensuring that the model is working as you expect. And then also, as new variations of data comes in that your model wasn't trained on, you can collect that new variation and then kind of start this whole loop over and over again. And from any point in time kind of in here, you might be starting this over and over again. So as you're training the model, you might be doing hyperparameter optimization. And so when you evaluate it, you see some improvements you can make, change that, rerun this. And basically, you can be rerunning this over and over and over again. In fact, you probably will. Once the model's in production, like I mentioned, you'll also be running this over and over again to make sure the model's working as good as possible. And when it comes to like LMs and really just any pipeline, there's going to be more steps in this. This is kind of like a bare minimum thing. But you want to, because you're going to be running this so many times and often at scale with like a lot of compute, you really want to make sure that this is going to be reliable and efficient. And that's going to save your engineering team a lot of time, and then also usually quite a bit of money as well. Fortunately, there's a lot of cool tools that make doing these steps way easier. You've probably used some of these before for like doing your validation and training models. Today, we're going to be using PyTorch, if anyone's used PyTorch before. And then kind of tying all these tools together, though, you want to build a workflow that is kind of the core of that pipeline, like we had mentioned. You want to build a reliable and efficient workflow for your application. Again, like I mentioned, you're probably running this over and over again. And a lot of times this project's going to be really big, and you want to have it scale up to meet the data and types of models that you're using. So you want to keep these things in mind. Scalability, you want to facilitate the scaling of your AI workflows to handle like your super large data sets and complex models. We work with a lot of people that do like really large image data sets, both in the medical field, also like self-driving. So that's a lot of data, and they need to spin up that compute and then also gracefully kind of scale it down when they're not using it. You want to have reproducibility. We ensure that your workflows can be consistently reproduced. This aids a lot in like collaboration and basically transparency between your workflows as you share them with teams. And both of those things, Flyte and Union, like we'll see that we're going to use today, is built on top of Kubernetes. So if you've used things like Docker files before that can consistently recreate your containers, we're going to be doing that today, but don't worry, you actually won't have to write a Docker file. We'll actually do it all in Python, which is really cool. And then you want to think about versioning. You've probably versioned your code. This probably makes sense already in your head. Typically in a whole pipeline, you also want to version everything going on there, like the data, the steps of what you did that data, the code, and then the model versions. This is really good for debugging on any type of team or any type of model, but this is also sometimes required in certain fields like finance or healthcare. We actually need really good lineage and traceability for everything that happened to get where you got that model in the place. You want to think about improved efficiency. So you want to allow your data scientists or AI engineers to really focus on the development piece and not really fiddling around with a lot of infrastructure ops parts. So we often hear like people, when they implement a modern pipeline, they go from something like doing experimentation from weeks to days and doing like model deployments from like quarters or months down to like weeks, which is really exciting. And then cost efficiency. You want to optimize your resource usage, your retries, caching, a whole bunch of stuff in your pipeline that can reduce the overall cost of developing and deploying your AI models. It's not uncommon that, again, when people implement a modern pipeline, they go from saving like over 50% or doing having like a 50% cost reduction, which is kind of wild. And it kind of blows my mind sometimes. And again, if you're doing this at scale, that can really mean like a lot for your company. I saw a couple questions from chat real quick. Someone said, is object detection and facial detection pretty much very similar under the hood? And for both, you have to pass in a decent amount of labeled images for the model and model to classify directly. There's different ways of doing facial detection. So you could do kind of a approach where you use object detection and what we're going to use today, and that might work good enough for some of your applications. But there's also different ways of getting more data. So like you could use something like an embedding model that actually looks at similarity between images that's not just like trained on different images. And I think that's what most people do for at scale object detection. But you could, like if you're doing something just for your personal project and you want to have something detect your face, you could use object detection. And then also if you're doing face detection, but not facial, like if you don't care about matching a face to someone, object detection works good for that too. But if you're trying to match a specific face to someone, you want some sort of similarity search type of thing a lot of the times, which can be like an embedding. There's different ways to do that. And also Ravi said, hello from San Diego. Awesome, welcome. If you just joined, we're gonna go through some code shortly. I'm just finishing up on some slides, but also if you wanna go ahead and start poking around on the code, the links are in the description as well. And then we wanna, so hammering on some of these pieces of like cost efficiency and improved efficiency, there's some things that really stand out that when people implement, I see them make a huge difference. And so I'm just talk about those real quick. Just like 4 of them. And again, so keep these in mind no matter how you implement them. Like if you haven't done this before and you're building out like a team right now or implementing a pipeline, these can make a big difference. You want to optimize for local and cloud development. So this might seem obvious, but not every team or tool is set up for you to kind of build a pipeline on your laptop and then do a more intense production run. So you could build a pipeline, debug it all locally without you having to basically kick off a cloud job every time you want to debug. So sometimes you'll be writing your pipeline, and then you want to see if it's working, and it has to spin up a container, then it has to throw an error, and then you have to go pull that error from somewhere, and that could take a long time versus you just doing it on your laptop, you might be familiar with. So being able to run this locally and then be able to kick off in a production cloud seamlessly can save quite a bit of engineering time. What was I going to mention? Oh, so you could even take, if you have a more intense model or big data set, but you want to run it locally and you can't actually train that model on your laptop efficiently, you can take a smaller model and like a sample of that data set, do a test run of your pipeline locally, and then kick off the production run. You want to leverage caching in your pipeline. So caching capabilities speed up the development cycle by avoiding those redundant computations. So if we're building our pipeline here, like we're going to see today, we'll actually see this implemented. We're going to train a model, but every time we do that workflow, we're adjusting some hyperparameters. We want to kick off this whole workflow. We don't want to download the data set or pre-process the data set again because those haven't changed here. We can cache those and then rerun the workflow and then kind of skip these steps and just take that state that was stuck there and then pull it into our model and then just run that task. This is also really, really interesting. So like we've been working more with people doing agentic AI, and spoiler alert, if you were here at the beginning, I shared the event for the 2.0 launch. So it's going to have some more dynamic stuff, and like leveraging caching or stateful retries is a huge thing too. So like if your agent fails in between and it's done like a lot of chain of thought reasoning, that was like a lot of tokens that it spent, it can kind of fail somewhere as it's calling a tool or something like that. And then being able to use a cache state from the previous thing and then do a graceful retry from there can save quite a bit of money on the LLM side. So if you're also thinking about LLMs, like a lot of people, I know I am, today we're doing computer vision, but a lot of this applies really to kind of any AI workflow. And even for agentic stuff, it might not be worded exactly the same here, but basically in those workflows, it's a lot of the same problems that come up. And again, if you have experience, let me know in the chat. It's always interesting hearing about like what people have experienced. Task level resource management and containerization. Being able to have precise resource attribution on each task can save a ton of compute as well. So previously, a lot of people have, if you built a pipeline like a long time ago, you might have had what I think it's the right term would be like a monolithic pipeline where like you have all these steps, but then you have basically one compute thing allocated for it. So when you train your model, you need a GPU, but when you're downloading the data set, you don't. You probably just need a couple of CPUs and some memory, and that process could be hours. And if you had a GPU assigned to that task or to all these tasks, that would be eating up that GPU time, which is either really expensive or hogging that GPU from your cluster for other people to use. So what we can actually do is have a precise container defined for each one of these tasks. And so here's like downloading the data set. This is just using a couple CPUs and memory. And so it's really, really cheap to run for that hour, potentially hours to download. And then our training task, we assign like higher resources, including a GPU. So we're only using this expensive resources when we need it. And then you can also look at this in production. So it's pretty common, and I do this too, where when I create my workflow, I kind of overassign the resources, and then I can actually look in production and say, oh, I'm actually like, I declared here 12 gigabytes of memory, but I'm only using 2. And I can then bring that down. And that, again, if you're running this over and over again at scale, this saves a lot of resources. And then the last one I'll just mention here is mitigating errors with type safety. If you've used other languages outside of Python, you've probably experienced this. This is just kind of a faster way to debug and basically debug before you run your pipelines. And also, this is also really good for sharing code between people too, and kind of more easily seeing what's going in and out of each task. So MLOps has a ton of opportunities for efficiency. And I put this with AMP promotions. It's pretty common when I see people go and implement like a modern MLOps thing, that they kind of get to have control of that team and implement more of these changes inside the company. So like I mentioned today, we're going to be using Flyte and Union. So Flyte is our open source. You can check this out here. And I see some questions in the chat. I'll get to them soon. We're almost to the code piece. So when we do the setup, I will tackle some of the questions in the chat. Today, we're going to use Union and Flyte, like I mentioned. So specifically, we're going to use something called Union Serverless if you want to follow along. I'll share the sign up link again, but they're in the description. I shared them earlier. It's free to sign up. You get $30 of compute credit. Basically, we make it really easy to do all those things we talked about just inside of a decorator on top of a Python function, kind of like you would already be writing. So here we have a parameter for cache is equal to true. You can give it a cache version, so you can change out those cache versions if you want. We're going to assign it a container image. Again, we'll see this in action, but this is taking basically a Docker container. So every time it spins up, it's going to be reproducible and the same environment. The cool thing about this too is Flyte has a thing called image spec where you can actually define a container specification in Python. So you don't even have to write a Docker file. You can just write it all in your Python project, and then you can use remote image builder in Union as well. So it'll check it to see if this image exists or not. And if not, then you'll go build the image and then pull it into the task when it's spun up. And then we have requests. So this is where we pass in the amount of compute that we want. Here's just saying CPU and memory, but then we can also add in GPU. You can also add in specific types of accelerator. So we make this really, really easy, basically, to get kind of that modern MLOps pipeline in place directly in your Python code. You have the declarative infrastructure. Every run is versioned as well. So every time you run that workflow, you'll have a version of it, and then you can roll back and go look and see and get that full lineage, like I mentioned, can be really important. I think it's great for debugging on any size of team or type of application anyway. So you can see exactly what happened to the data, all the steps, and then pull any information out of that. And we also enforce typing here. It's super flexible. There's a big plugin ecosystem, but also just runs kind of Python instances. So most of the time, you don't even need a plugin to use whatever tool you want. It's scalable, built on top of Kubernetes, and then you get a pretty nice user interface and API that, again, we'll see in action here shortly. And Flyte's used by thousands of companies in production. In fact, most people here, actually, if not all of you, have probably interacted with a machine learning model that was trained on Flyte, whether that's like social media, listening to music, or driving a self-driving car. You've probably actually interacted with a model that's used Flyte to train it in the backend. So we're going to go on to the code. Again, sign up here if you want to follow along. Free to sign up. It might take 3 to 5 minutes for it to approve you. And then this is going to be a link to the GitHub repo. And then specifically, when you get to that repo, you can click the Open in Collab button here, and that should take you to this. And I'll just share the direct link as well. So this is going to be Collab Notebook. I think you need a Google account to run it. I assume most people have a Google account. Let me close this out. And then what I like to do is actually save a copy in Drive, but you should be able to run it directly from here too. But if you save a copy in Drive, then you could do edits and actually come back to any of the edits that you have. And then I'll tackle some of the questions and show a little bit more of the platform as we're installing this. So once you have your own copy or this opened up, let me actually zoom in a little bit. Go ahead and run this first code cell. You can hit this little play button, or as the code cell's highlighted, hit Shift Enter. And this is going to install the libraries that we need. It should just take a couple minutes, I think. Which also, we're using UV pip install. It really speeds it up because it can run multiple installations in parallel, which is great if you haven't used UV before. And then I should have had this up. We're going to basically build this pipeline here. Here's an example of the nodes, but we'll have this graph here. We're going to download a data set. We're going to download a model. Then we're going to train that model. We'll verify our data and annotation so we can actually embed information in these really neat little decks. Any HTML or Markdown can go in here, so you can actually use like Plotly and interactive charts in here as well. So again, this is really good for the lineage piece to go see like, well, what did my data look like before I train my model? And as a side note, I always recommend looking at your data before you train a model, especially with computer vision. There's been a lot of times where I swear that I was reading in the data correctly and the annotations correctly, but then when you verify it here, you can see that something is wrong. So I always like to have this step. It's very, very useful. then we'll evaluate our model. Again, we'll embed this in a deck as well, so we can actually see these are predictions that we're going to get. If you scroll down, then we'll get some other like accuracy metrics and stuff per image as well. In our train model, we have another deck. This shows what the training looked like. And inside here, you can also see that we have like a version of all the code. You could pull this down with the SDK as well. But again, you get all the versionings. Every task has inputs and outputs. So again, this is all version. You can go trace exactly what was going on. And then this is going to generate a artifact that is going to be a model. And then we'll see how we can actually pull this model down locally and how you could theoretically run it on a Raspberry Pi, but we'll also run it locally on some images in a video. And then we'll also show that we can actually launch this as an app and how to interact with the app on Union as well. So we'll also serve it, and you'll come away with a Gradio app with your model running as well that you can share with people or use as a portfolio piece or something like that if you want. So we'll actually see different ways of interacting with the model when it's done. My app was spun down, so it's spinning back up right now. So again, I'll give everyone a couple of minutes. I shared those links already. I'll share them one more time. I'm just guessing that people probably need this account. And then the Collab. While that's going, let me catch up real quick on some of the chat messages. And if anyone has any questions, let me know. And if someone wants to let me know that they were able to open the notebook and are kind of ready to go, and that maybe, oh, the installation's already done. Yeah, UV makes this so much faster. Actually, let me do one more thing before I go to the question. So the next step, once you do this, and if this worked for you, everything should work hopefully very smoothly after this. So once you are logged in, and then you ran that first code cell, then installed everything, scroll down to this authenticate section and run this code cell that says union create login serverless, and then run that. This should generate a URL for you to click on. Click on that, hit next, and then our notebook environment should be authenticated now, and we can run everything on compute and get all those features like we talked about, including GPUs to run and train our model on. And if you want to, by the way, you can keep running the code cells. I will be walking through everything though. If you run this next code cell, this will actually kick off the code. So actually, let's do this, and then I'll walk through all the code and questions, because this can actually take a little bit for everything to run. So this next code cell, once you're authenticated, I'll walk through all the code of what this is calling here in a minute, but this can take a minute or several minutes for it to actually run. So we're saying union run remote, and then they're pointing at this path, workflow, train, faster RCNN, pipeline.py, and then we're calling a specific function in there. Again, I'll go through all this code, so it's okay if you don't know what this is calling yet. And they were passing in a parameter of saying 10 epochs. So this is going to be us training our model. It's going to be looking at our full data set 10 times. Run this. And then for me, because I ran this previously, my container image should already be built. So it's actually going to go ahead and kick off the training job pretty quickly. So it's running an execution on remote, skip building because I already have my image. For you, because it's your first time running, it's actually going to go ahead and build that container image. Then I get this URL I can click on, and I can see that my pipeline's running. The download dataset and download model are already done because I read them from cache. So every time I run this workflow, which I can relaunch from the UI or the CLI, it's going to now read that in for cache. And I can see that it says output for this execution was read into cache. So yours will take a few minutes before it gets here. But then you should get something that looks like this once your container image is built. So while that's going, one, people let me know if you were able to do that. Like if you're able to log in, if you are able to run this. It's again, we'll go through all the code here in a second, but if this is running, let me know, because that's a really good indication that the rest of the workshop should go really smoothly for you. Let me catch up on chat. Someone said, this is great. They've never done caching. Awesome. Yeah, it's very, very useful. Again, like I mentioned, in a lot of different applications too, or having stateful or like graceful retries, like if it fails and you have a cache state, you can automatically retry from that state. That's really, really beneficial too. And like we mentioned, that's a big problem we're seeing right now with like agents. But for any pipeline, cacheing, if you're running workflows and you want that full lineage, and you don't want to rerun those parts again, makes your workflow way more efficient. And you usually see a big time speed up and usually quite a bit of cost savings as well. Someone said, how do you share GPU between machines and Kubernetes cluster? I used to think GPUs used to tie to the VM. I'm not the biggest behind the scenes Kubernetes person, so this is built on Kubernetes. I use this quite a bit. I think for the cluster though, I don't know if you share a GPU per on different clusters. I'll have to double check with that though. But I think in this case, well, you can actually, sorry, you might be talking about per task here too. So there's actually some things where you can do GPU, what's the word I'm looking for? Is it sharding? Where basically you're splitting up some GPU resources per VM. There's some stuff around that. There's a little bit built into Union or Flyte, but there's also ways that you can use other libraries that do this well. Like I think Ray is a popular one for a fraction, so fractional GPU usage per task. You can do that with a couple of different ways. One, using like libraries, and then there's a little bit built in if you look at the docs of using like portions of an A100 inside of a task. That might be what you're asking. All right, chat is a little too quiet, but I see a lot of people here. So does anyone want to let me know, is this working? At least one person in the chat that you're able to follow along, that you were able to sign up. Did you get onboarded? Are you stuck? Someone said it is. I'm guessing that it's working. Awesome. Okay, so we ran this. Like I was saying, you might be building a container image. Basically, that's setting up a environment for you that you can reuse with the packages that we need, but also kind of basically the exact package and Linux environment that you want for every type of container. So I said, what do we do with the image? So the I think we'll see this as we go into the code here shortly. We'll see what's going to happen with that image and even how it's kicked off. So it'll make a lot more sense if I just go in the code. But if you still have questions about it, let me know. All right, so we ran this, and if you want to, basically all the code is in the notebook. You can see this is the path of where it lives. Basically, what we did was we downloaded this GitHub repo. And we can see there's this workflow folder, task folder. You don't have to do this part if you want to. I'm just showing where the code lives. And if you click on this, like this is inside task, we have this data.py. And then we have a workflow.py. And basically, we're going to be looking at these files. But what I did to make this easier for the workshop is actually embed them in a code cell. And this write file function is a magic function of a notebook where I actually write the code in here to that location that's right here. But we downloaded from GitHub, the GitHub repo, so they already exist. So you don't have to run this code cell. This is just kind of showing the code there. I couldn't find a better way to do this in a notebook, but this is the easiest way I could find for kind of showing the code all in the notebook, but just know that this code already exists kind of in .py files in these folders where these paths are here. And that's what we did here. So we call this workflow train pipeline, and there's a function in here. So we'll see what that looks like here. So we have this workflow pipeline, and basically a workflow, each one of these nodes is a task, and a workflow is the collection of tasks and how the data flows through them and how they trigger each other. So workflow decorator is what we're going to use here from Flyte. And then we're defining this function, faster RCNN train workflow. By default, it has these parameters that we can overwrite when we call it. So it's going to, by default, train on 3 epochs, but we saw we passed in the parameter of 10. So it's actually going to look at our data set 10 times. And the number of classes by default is 3. You could overwrite this. So if your data set that you train later has more or less than this, you can overwrite this number. And then by default, I don't have the string in here, but if you want to upload your model file instead of having a union artifact to the Hugging Face model repo, that's an option as well that we'll see in the task later. So then we're basically calling these tasks, which we'll look at this code again, but we're importing these tasks from the task folder. And again, we'll look at all this code. But basically, these are all the functions like downloading a dataset, training a model. We're importing those in, and then we're saying how the data flows through them. So first, we're calling this download dataset. So we're assigning that to this variable dataset directory, and then we're going to pass that into the verify data annotation task, as well as the train model task. And again, we saw these tasks here. So like this is the verify data. Once we download the data, we're going to pass the data into there. Now, keep in mind that each one of these by default is a container. So that means that it's going to spin up compute and then spin down. If you've never worked with containers before, it's a little bit interesting because if you download a data set, for example, and you spun up compute and then you spin that down, well, that data set no longer exists in that container. So you have to write the data out in a way. And Flyte makes this really easy. We'll see this in action in the next code cell. But basically, you assign it as a Flyte file or Flyte directory. And basically, when you return something out of a container, it'll assign it to a blob storage or save it to a blob storage. And then you can read that into all the other tasks. So we make it really easy to work with the containers here as well. So we basically define that workflow that we saw. And then let's look at all those different task files. Actually, first, it's the container file. Sorry, I forgot the flow. So they're talking about where we use the image. We'll see that using the task, but this is how the image gets defined or created here. So from FlyteKit, that's the Flyte SDK. We're going to import image spec and resources. Or I guess image spec is the only thing we need here. Image spec is the thing I mentioned where instead of creating a Docker file like you've done before, you don't have to do that. You can do this all directly in your Python project. So we're just going to assign it to a variable here called container image. We're going to call image spec. We pass in a name for that container, the requirements. So you could put the package requirements directly in Python here as well, but instead we're reading from a requirements.txt. So this makes it really easy to set up locally, but then also set up the container and have them kind of mirror each other. You can add in a extra index. So this is going to look for a specific version of PyTorch with CUDA 11.8. Image builders union. This means that when you kick off a task, like we'll see down below, it's going to reference this image. And if it doesn't exist, then it's going to build that image like we just saw if you ran above, and then pull it down. And if you don't have this builder set to union, what you can do is set up Docker locally and then build the image locally, save it to your own image repository, and then pull it in. And then you can add in specific things in your environment like CUDA versions, but also different specific packages like C++ or a C++ builder. You need this if you're going to do like quantization. And I think in this case with OpenCV, we need it as well. And then these are our requirements here in our requirements.txt, Union FlyteKit Torch, Torch Vision, Matplotlib, PyCoco tools, datasets, Hugging Face, Hub, Python.env, and then OpenCV Python. And we'll just talk about these kind of as we use them. And let me see, I see some questions here. Again, you can keep going through the code. I do want to make sure I try to answer most of the questions, though. Someone said they're doing the authentication. Someone said, can you go over kind of traditional, less efficient way that companies have been going about their data pipelines, or someone, as someone who hasn't built a data pipeline before? So I think like kind of, I'm not sure if you were at the beginning, and like I'd mentioned, one of the things where like if you don't have things like caching, or if you don't declare specific resources per container, which we'll see here. Actually, if we look at this code, this is in the data.py, we have our first task, which is downloading a data set. So we have our Python function, kind of like we would normally have. We can see that's actually going to return a Flyte directory, though. That's where I mentioned there's going to be a persistent storage of the data that is returned here to like basically like S3 bucket or whatever you set up in your data plane. And then we have in our decorator the container image that we just defined above. So it's going to see if it's built or not. We have enable deck, so we can embed visualizations if we wanted to. Caching is equal to true. So every time we run this workflow, it's going to look and see if this is cached and then not rerun this task. And then here's the request. So like in your question, one of the things that people didn't always have before or don't always have set up right now is like this resource specific thing per task, where, like I'd mentioned, if you need a GPU in your task, like if we're going to use later for training, if you called this now and are downloading a data set took a long time, then that would be like a pretty inefficient way to do this. And if you didn't have caching and this reran every time you ran the workflow, basically, that would be a pretty inefficient way. So basically, again, we're just adding these Python decorators to our functions and then getting a lot of those kind of abilities that we talked about at the beginning. Also, if you weren't here and you want to look at the slides, I think this should be able, I think you should be able to view this. And that goes through kind of some of the steps. Right, so we have our download function, we have our decorator on top that we pass in all those parameters, download Hugging Face dataset. By default, this is going to be the Hugging Face dataset that I have. If you bring in your own dataset and you want to write to Hugging Face, which is Hugging Face, a really good hub to store models and datasets in, and you can easily pull them down. You can think of it like GitHub, but for data and models. This is the repo where this is going to live at. So you could overwrite this with your own repo if you end up saving to Hugging Face. And then we're just going to import snapshot download from Hugging Face Hub. We're going to write that dataset out to a local directory. And then we're going to return this as a Flyte directory, basically. And like I mentioned, if we go look at this task even here, the input was just the repo ID. So again, if you have your own later, you could adjust this to be your own repo ID. And then the output, this is a URI of now where that data set is going to live that we could reference into other tasks and then download it. And we have our visualize data tasks. This is the one where if we go back here, we verify that our annotations and images were read in correctly. So again, we have a task on top, passing in the CPUs and the resources that we want. So 2 CPUs, 4 gigabytes of memory here, enabling deck that allows us to get that clickable button with HTML that we can embed in there. And then we are basically just downloading the data set we previously downloaded into our container here. Inside of there, we're looking for the image directory and then also the train.json. So usually when you do annotation, you get images and then a JSON file that contains the annotations, like pixels where those bounding boxes belong. And you want to be able to read those in, and then basically your model is going to read in annotations and learn from what's in that bounding box. If you click in here, oh, sorry, we actually don't have it downloaded here. It's downloaded in our union. We'll download it later so we could actually see what this JSON file looks like if you're curious. And then it's going to read in the first 9 images. And then basically we're just going to, like, this looks like a lot of code here, but we're just looping through those 9 images, getting the annotations and the image for them, and then drawing those bounding boxes on it with matplotlib. And that's what's going to give us that visualization here. And then again, this is kind of a sanity check just to make sure that bounding boxes are around the objects as you think they would be. Otherwise, if this looks wrong or like the bounding boxes are squished or run in a different way, that's a good indication your model's not going to learn because you messed up reading the data into your project. Like I said, I've had that burn me many times, so I always include that type of step now. It can be very, very useful. We're basically just saving that matplotlib grid as an image, and then we're going to embed it into this HTML report that you can make in Python, and then we're going to append it to the deck. So we initialize the deck here with a title, and then we append the HTML report, and then we're going to make it index 0. And that's how we get at the, in our deck here, at that very first tab, we have our report that we just created. So again, you can do this with any type of data, though, which is really exciting. Or like different types of things like Plotly have actually interactive charts in there. So those are our first kind of 2 data tasks. And let's go into the more exciting one, which is going to be our task for our model. And let me get a drink of water real quick. Let me know if there's any questions while I'm doing that. All right, so now we have our model tasks, and this is going to be our training model, our evaluate model tasks here. So again, it looks like it's going to look like a lot of code sometimes. A lot of that is, again, just like doing visualizations and looping through our kind of training piece. So don't be afraid if you haven't used a lot of PyTorch before or anything like that. We'll go through it. And I'm going through maybe at a little high level sometimes because I do want to try to get through all the content. But if you have questions, let me know, and then you should have a copy of the code that you can go kind of look back on as well. So first, we're going to define artifacts here. So this is going to make it really easy for us to, like when we train our model, we can have an artifact that can be easily shared across teams and across tasks. If I go back into Union UI and I can go to this artifact tab, I can click in here. From here, I could add a card. I didn't with some more data, but I have this lineage tab. So I have now a model that we're going to train here and use in a couple different applications. But if I'm debugging and I'm wondering like where this model came from, I can click in the artifacts. I can pull this down and can actually just click back on here. It go to the exact version of the workflow that this model got generated from, which is again is really useful for like debugging and looking at everything that happened here. So I could actually go see like, well, what was the data set used to train this model, et cetera, if I'm kind of trying to get more information about it, which is really neat. So we're going to define an artifact. We import artifact from Union. We give it a name here, and then we'll reference this when we create it. So first, let's download our model. So again, decorator, just like you've seen before, that's at task. And then we're going to say cache is equal to true. So every time we run the workflow, we don't want to re-download the model because basically we're taking a pre-trained model and then we're going to fine tune it on our own data set. So every time we rerun this, we don't need to take the pre-trained model again. We're just going to take that cache state and then fine tune it on our data. And for this, for just downloading again, we just need CPU and some memory. We have our download function here, and it's going to return. This is the way you return the artifact right now. Is annotated is a specific type inside Python that basically is a type with metadata. So it's going to be a Flyte file. Like I mentioned, this is a file type that gets serialized and deserialized between tasks and written to a blob storage that you can reference. So outside of your container, once the container is spun down, you could pull this into any container or download it or do anything you want with it. And then this is our artifact name that we gave it above. So again, just going to contain metadata that gets written to that artifact area. And then we're going to assign a variable called model. We're going to look at Torch Vision models detection, faster RCNN and MobileNet. Now you can look at the Torch documentation. There's different types of object detection models. So if you want to use something different that's not the MobileNet faster RCNN, then you could look at some other model types there. And then we're going to save our directory to here. .pth is basically a PyTorch model type. So we're saving faster RCNN MobileNet pre-trained model, saving it there. And then we're creating an artifact, then we're returning this out of this function. And it is creating artifacts that will have like this pre-trained version, and then we'll also create an artifact of our fine-tuned version as well. But it's also being returned. So inside of our workflow here, we download our model, and then it's coming out of this task, so we can then just easily pass it over to our train model task, which is our next one we're going to implement. So again, our task decorator here, container image, enabling deck so we can look at the log of the loss and accuracy over time. And then here's where our requests resources gets maybe a little bit more interesting. Is we add a GPU. So by default, when you set up Flyte or Union, you can say what GPU is by default. In serverless, the default is an L4. But you could overwrite this. And in serverless, in the serverless cluster, we have A100s as well. So you can actually look at the docs and see how you can declare specific accelerator types and kind of overwrite what the defaults are to pull it in. We have our train model function. It's going to take in a model file, a data set directory, the number of epochs that we want to look at the data set, the number of classes. So in our case, it's 2, because we have the Flyte sticker and the Union sticker, and then our confidence threshold. So when you do object detection, you'll see this a lot, that they all operate slightly differently, but basically want to give it a confidence threshold to say only draw a bounding box if you're like, in this case, 75% sure that that belongs to that class. Otherwise, if this is really low, you'll see that it draws a ton of bounding boxes. And so I like to give it a confidence threshold when I'm training to look at like validation. Otherwise, it'll draw a ton of bounding boxes and you'll get really low accuracy or IOU. So with object detection too, let me actually pull up this. I should put a slide for IOU here, actually. Basically, IOU is the intersection over union where the bounding box, the ground truth bounding box, how closely it relates to the predicted bounding box from the model. And the closer they are, the higher the number is, and the further apart they are, the lower the number is. So like if it's predicting a bounding box is way out here, even though the ground truth one that was here, you'll get a pretty bad number from it. So I like to add a confidence threshold to try to get like one bounding box written per class prediction. And we can actually see this later. If we lower it, we'll get like a lot of bounding boxes returned versus kind of the clean predicted ones here. So I think this is with confidence threshold. I think actually log it 75 here. But if we lower this, you'll get like multiple bounding boxes sometimes around per object. So this will just kind of throw off your evaluation report, because in production you will set a confidence threshold again. We'll see this later too when we write out our predictions. And then we're going to validate every epoch, but you could do this like every 10 epochs if you're training for a lot more than we are just during the workshop. And then number of classes is equal to number of classes we passed in, which is 2 plus 1. So it's pretty common. And this will depend on the model, though, that your data classes should be the amount that you're going to pass in. So we have 2 classes in our data set, but then you add 1 for the background. And that's how a lot of object detection models work. We're going to print out the confidence threshold that we're using, the number of epochs we're going to assign, the best IOU. It's going to start at 0, and then we'll see how our predictions do over time. We're going to write our model to the models directory. We're going to use CUDA if it's available. So it should be, we have a GPU instance here, and we set up our container to have CUDA 11.8. CUDA is basically NVIDIA's API to work with the GPU, like when you're training a model. We're going to download the data set. We're going to create the model directory folder. And then we're going to create the local directory for the data set. It's going to be downloaded into this container. And then we're going to load in the data set here. So it's going to load in those images, looking at the annotation file. Again, we can look at this later when we download it locally. But again, just think of this as a set of images and then a JSON file that kind of has a name for each of those images, and then the bounding boxes for each one. And we're going to do this also for the test data set. And for this example, we're kind of cheating. We're going to reuse the trained data set, because I just took a small sample size and I need to go label more to actually do this a little bit better. So when you're training your own or actually putting this in production, you would have a trained data set and then a test data set. And basically, what we want to do is the model is going to learn from the training one, and then you use the test data set to do evaluation on to make sure that it's learning appropriately and actually making predictions correctly on images it's never actually seen before. We're going to cheat a little bit here and just reuse the trained JSON, but usually you'd have like a test JSON or a validation JSON. You would pass that here. Then we're going to load in our model that we downloaded. And then this is something that, again, if you use a different model, you would have to change this slightly. But basically what we're doing is this pre-trained model is trained on the Cocoa dataset, which has, I think it's like 81 different classes. And you might have seen this before. It's like bike, sheep, a whole bunch of random things in there. What we want to do is we take that and we basically are cutting off the prediction layer of that model that have those 81 classes, and then replacing it with the amount of classes that we want to predict. So our case, it's just the 2 or 3 with the background. So basically, we're changing the shape of that neural network to now just predict out to 3 different classes. And then we're moving that model to device. Basically, again, this is a convention inside PyTorch. Like we assigned our device to CUDA before, and then if CUDA is available, it's going to move it to the GPU. And then sometimes you'll need to move this back and forth from the GPU to CPU, depending on what you're doing. There's some other stuff for deep learning, like other parameters that you can set for optimizations. We won't go too deep into this, but like you have learning rate, basically how big of steps your model takes to fine tune on the new data. And then we're going to have this evaluate model. Again, like we were saying, this looks like a lot of code, but really here, we're reading in the current state of the model. Again, we set it so it'd be every 1 epoch, but it could be whatever amount that you want. And then we're going to loop through, do predictions on the test data set here, and basically read in the bounding boxes and the category ID from that JSON file, and then basically calculate how correct the current state of the model is on the test data set. So we calculate the IOU. Again, that's intersection over union, kind of like I explained a little bit, like you have the ground truth label and then the predicted boxes. And then we go through, sorry, that was our evaluate model. And then after, or sorry, we have the evaluate model function that we can call, but then outside of the evaluate function here, basically we're just going to go through every epoch. So remember, we passed in 10. So for each one of those epochs, we're going to go ahead and calculate the loss. We're going to read in the images, read in the bounding boxes from that train.json, and then basically do our deep learning from it. And a lot of this, again, like I mentioned, is then some things like plots. So here we are plotting out inside of our train model. If you go to deck, we have this this plot. This is our training loss where it started. If you haven't done deep learning before, you usually want to minimize your loss and then get your accuracy up. So here is our loss value, and we see this went down over 10 epochs, and it looks like it's still going down. So if we train for more epochs, potentially our model might even get a little bit better. And then our accuracy already started out pretty high here. Again, we were kind of cheating because we were using the trained data set for both test and training here. And we see our accuracy, which is just the class prediction. And then we have the IOU, the intersection over union. That also improved over time as well. And let me keep going. So then we'll go look at our evaluate task here, which again is this one. So now we have let me talk about the train model getting saved real quick. So we are basically then returning out of there the fine-tuned model. That also gets created as an artifact. So now that we can reference this fine-tuned model across different tasks, or even pull it down locally, which we'll do here in a second and actually run. So one more task, though, before we pull down our model and actually get it to predict bounding boxes is just the evaluate model function or task. So we're reading in our model and then a dataset directory, and then which is a Flyte directory, and then we're passing a threshold. So again, you could overwrite this to a different value. Again, we're looking at CUDA, so it should be running on GPU for this task as well. We can see that we pass in a GPU again because we're running predictions. So you want to have the GPU for training and usually running. Although, like we'll see later, our model is actually pretty efficient and can actually kind of run on a CPU pretty good. So we're going to download the data set again, and then we're going to pass our model to device. We're going to set it to eval, so this way it's not going to train it. We actually just want it to run predictions. We're going to, again, create a grid of 9 images. And then, again, this is similar to like we've seen before, taking we take our model, and then for, in this case, the batch of images, we're going to read them in, get the boxes from the JSON file and the labels from the JSON file, and then do predictions on those and see how well they coordinate with each other. And this is all just looping through those and plotting them out. So it looks like a lot of code here. Again, this is just kind of some fancy stuff to plot out each of these bounding boxes that you see from those predictions. And then our little metric score here. And then there's an optional one where you can upload to Hugging Face Hub if you want. I'll skip this for now. We're not actually using it for the workshop, but I did throw it there if people are interested. All right, so I might have gone through a little high level there. I want to go through, make sure, because we're already an hour in, that we can now run our model. So I'm happy to go back and look at some stuff. And then also, like I mentioned, you have the code that you can go run through or go back and look at it yourself too. But basically what we did was we downloaded our data set, downloaded the model, trained our model. Now we have this saved as an artifact that we can use in other tasks as well. And we are evaluating our model. So if we looked at it, we can see that the predictions look pretty good. It's kind of hard to maybe see here, but they have a class of 1 or 2, and then a value to them. That 98 is like the confidence threshold or confidence that model has that belongs to that class. And then this is our evaluation report where the mean IOU is 92. 1 would be perfect. So again, that's kind of the offset of bounding box prediction versus the ground truth one. And then the accuracy was 100. That just means that it didn't mispredict a class here. And you can see that for each image. So now we can go ahead and use our model locally that was trained. So let's first download the data set that we can use. So we're going to run this on an individual image and then also full video. So we'll generate basically this video that you saw at the beginning. So this is downloading a data set that we can use here. Let me catch up on some questions. Someone said, once the dataset loads, then we should be able to verify annotations in UI. So yeah, even if you end up not using a UI or anything like it, it's always good to have some sort of verification step that you can look at. So I always write out the annotations like this just to make sure. Like you could have the classes here too, but usually just a sanity check of making sure that like bounding boxes are written around the images is good enough for me. And then also you can see what these images look like. So sometimes they might be flipped or something like that. Like if you, for example, actually I ran into this problem. If you take images like vertically with your phone and then you read them into PyTorch, by default, it flips them horizontally. So it's just, and I didn't know that. and then because it did that, it didn't flip the annotations. So the annotations were all wrong. And that's just an example of a recent time that it happened to me, even though I feel like I've done this for a long time, but it was like I didn't know, I never done a vertical image, and I was helping someone with their project and it automatically flipped them. So it was just another time where I was like, oh, you read in the images look different than you thought they were going to, and then the annotations are wrong because of that. So stuff like that will happen all the time. So it said the code of data loading and annotation verification has been successfully run, but you're not able to see the images in the UI. Oh, interesting. Like you can't see them in this deck. Do you have this deck button? So you should see, oops, let me zoom out. You should see something that looks like this now. You have this node view, this graph view. And then you should have this verification one, and then there should be a deck button that should pop up. If not, there could be a bug specifically in serverless maybe. Okay, so I'm going to keep going in the notebook then. We have downloaded this data set now. So if I click in here, we can actually see that inside this folder, there's a data set. This is what the JSON file looks like that we've been using in our training as well. So we have an image path and then basically some metadata around it. And then these will all have basically points for the bounding box as well. And this is what the model was using to read in bounding boxes to learn from. And then we have images in here. So we can look at these images and then do predictions on them. And that's what we're going to do in this next code cell. So we're going to, first we're going to download the model. Then we can use the model. So here, we're actually going to download it as an artifact. So like we said, this is stored now in Union. You can pull this down. We're defining the artifact like we did before. We're basically going to do a query on that artifact variable that we just set, but it's looking at this artifact name. And when we call .query, this is going to pull in the latest version, but you can add a specific hash too. So like we mentioned, every time you run a workflow, like if you rerun this, if you relaunch this workflow from the UI, you're going to get a whole another version of this. And you can see that this is the workflow version hash here. So if you want to pull in a specific version of anything, you can take that hash. If you go look at the artifacts tab, you can see each one of those has a hash as well. So by default, .query is going to pull in the latest one. And that can actually be pretty useful to have by default, because like if you have this running on a Raspberry Pi, every time it starts up, you want to pull in the latest version or something like that, you can. But you could pass in a specific version if you want to. Then we're going to initialize remote. And basically, again, just pull down that artifact here, read it in as a torch file. And then in this case, we're actually going to set it just on a CPU. As we'll actually see that you can set up Collab to run with a GPU runtime, but by default, it's using a CPU. And we'll actually see that it doesn't take too long to run on the CPU because our model is actually a pretty efficient object detection model. Now here's the code cell where we'll actually do the prediction. So I'm going to run this, and then I'll walk through what's going on here. We are reading in we're setting the label. So 1 is equal to union sticker, 2 is equal to flight. And then we're, again, looking to see if CUDA is available, but it is using CPU here. Setting a font that we're going to grab from Google Fonts. This is just to kind of write out the labels inside of our annotation. We're going to then have a function that's going to draw the bounding boxes. So it takes an image, takes in the box annotation, coordinates, labels, score, and then a label map. We're going to call draw from Pillow, which is a library that we imported here. Pillow is a really cool library for Python, where you can draw like bounding boxes and do a lot of other stuff like draw fonts and stuff as well. We're going to actually make some pretty bounding boxes here. So a lot of times you'll see with examples, people come away with kind of like a ugly, crudely drawn red box or something like that. And I'll actually show you how to make some cool bounding boxes. You can set colors. So these are RGB values and opaque values. So here we're going to set it to blue, and then I think it's like yellow, actually, not orange. But you can adjust these RGB values that you want. This is the box around it. And then this is going to be the actual fill of the box. So we're actually going to fill the color, or fill the boxes with some color as well. But if you wanted to, you could remove this or set this to 0, and it would be completely opaque. And then for the boxes that are passed in, we're just going to draw them out with this draw rectangle. And then we'll get an image return. So then we're going to pass in a specific image that we downloaded and basically just run that function. And if I open up this folder now, which you can as well, if you ran that code cell, you should now have this output image.jpg. And then we got this prediction. And I accidentally have the font size really small here, but you can see it does say flight sticker 98%. We get this cool green, I guess green, not blue is what we set it to. And then this is the blue one down here, union sticker 91%. So you train the model. You also train it with a production grade workflow, like I was saying before. And it's okay if like some of the concepts, like it went pretty fast for this. It's a lot to try to cover in like an hour or a little over an hour. But you were able to train a model, pull it down locally now. I mean, it's local. It's in this Collab Notebook. You could run this on a Raspberry Pi and pull that model down locally and then run it on an image. Let's go ahead and run this on a video real quick. And as this is running, I'll go through the code, but I'll also just mention this code cell next here won't run in Collab. But if you actually want to take this model that you trained and run it on like a Raspberry Pi, here's a script that I use to run on my Raspberry Pi. Basically, it's going to download the model like we did before. And then it's going to access the webcam. And then it can actually start running this live on a webcam, which is pretty cool. So it won't work in Collab because I don't think it has access to your webcam here. But we'll see quickly below how to deploy on Union and then actually access our webcam and see what the prediction does in this case. But for this one, we can actually see. So again, we're running on CPU here. And it's actually able to already take a video and run that whole model on it and then write it out. Basically, this is just the path to the video. Get some metadata around it. And then we have this video writer. So it's going to save it as object detection video.mp3. We have this function that's going to run inference. Basically, it just divides up the frames and then runs the function that we defined above that writes out those bounding boxes on each frames and then stitches them together. And if you ran this code cell and you go back to your folder, again, you can get to it by clicking this little folder icon, going to this folder here, and then going to object detection video.mp4. If you double click on this, it should download. And if I open it up, now we have a pretty good looking video here of our object detection model running on our video. And you can see it's not perfect. Part of the reason is in our data set, if you go look at it, we don't have all the variations of like stickers flip certain ways. So actually like this one is sideways. I don't think our model ever saw it sideways before. And we'd want to have variations like I talked about at the beginning. It's actually pretty important to have all the variations of what your model's going to see for it to learn from. So we can see it's doing really good on these flight stickers, these union ones. We could have more examples with more variations and it would really improve our model here. But this is really cool. We get this pretty looking video that's awesome to share out, by the way. If you train this on your own data set and you have this model, it's a really good kind of piece to put on like your LinkedIn. People love computer vision models running on videos. So you went through, or you could go through later, train your own model on your own data set, and then come away with a really cool video that you could share with it. One last thing I'm going to go through is you can run this code cell. We're going to call union deploy apps app.py and then give it a name. We'll look at the code here. So again, if it's your first time running it, it might have to build an image here as well. So it might take a few minutes. Basically, we have two files that, again, they already live in this folder. We have this app main.py and then app.py. And here we are defining our artifact because we're going to pull in our artifact and now serve it on a web app. We have image spec, so this is a little bit different than our previous container image. We're defining it directly in our code here. So like I mentioned, instead of using requirements.txt, you actually can specify the packages directly in Python here as well. And then any other specific apt-get packages you need. I think we needed these ones to run with Gradio or OpenCV, like we'll see here shortly. Specific CUDA versions, etc. Then we're defining an app inside Union. An app is a place where you can serve models or have an endpoint. And in this case, we're actually going to serve a UI and a model. And we're going to call it faster RCNN object detection Gradio. Gradio is a Python library that makes it really easy to write a UI around, specifically it's designed around doing like experiments with models. It's really cool. We're going to say every time this app runs, it's going to download model. It's going to call that faster RCNN fine-tune model.query like we saw before. So it's going to always pull down the latest version of the model that we just have here. And then we have some specific parameters around our app. So if you've done any deployments before, some of this might sound familiar to you. When we have our container image, like before, we have a port that's going to be served on. We have another code file that's going to be included here. This is actually our Gradio app. We'll look at that next. These are the arguments to kind of launch that app. And then we have these limit resources. So this is similar to like the task decorator that we saw before in our tasks, but instead now this is for serving, and you have limits and requests. So basically, we're going to request that each version of this app is going to be served on 2 CPUs here, 8 gigabytes memory, and then 1 GPU. You could set hard limits as well. So you want to request a certain amount, but then you can have it scale up a little bit more. In this case, we're setting hard limits to be the same thing. Accelerator here is actually going to be an L4. So we're actually defining this explicitly. By default, it is an L4, but I'd mentioned like you could import A100s, do that too. And then min and max replicas. This basically means this is going to scale down to 0 when an app is not being used after more than 2 minutes. You can set this to be longer. That means you're not paying for those resources if no one is using it. But then when someone visits your app for the first time after 2 minutes, it's going to have to take some time to spin up. But it's pretty common that you have some sort of scale up and scale down metric. So by minimum, maybe you have like 1. So there's always a version of your app running. But then when more than 2 people are visiting your app at the same time, then you spin up another replica. And so you basically have all these scaling metrics really easily defined, again, directly in your Python project here. And then this is our app main.py, which is the Gradio app. Basically, we're just downloading the model here, setting it to eval like we did before when we were doing predictions. We gave it a label map here. And then we have a function of detecting objects. This is just like we've seen before too. We're reading in the image, writing out the bounding boxes here. And then we have a Gradio interface. Let's see if my app is up. If you go back to the Union UI, you can go to apps. Mine says active. Yours may or may not be already. You get some logs, some overview. If I click in and click on this endpoint now, I have this app here. And Gradio makes it really easy to interface with, like, you can either upload an image or you can access your webcam. So you click this little webcam button, click access, and then, oh yeah, I forgot this works while I'm streaming too. Great. So here, if I click on this, it'll take a photo. I look great. And then I can click submit, and then this will run predictions on it. And let me actually, give me 1 second. I have a Union sticker. Let's see if I can get it to predict here. Hit clear. Let's see, it's not trained in this variation. So let me open this up real quick. I won't be surprised if it doesn't predict it, because like like I said, we need more variations in our model. This is different background than it was trained on, different lighting. And our data set that we trained on is really small. Let's see what happens though. Get it close. I'll take a photo. And then let's see if this catches it now. I might need, wish I had a Flyte sticker with me. Let's try one more time. Like, well, it got a Flyte. So the model's working here. Like I was saying, it just isn't the same variations that it was trained on. So it's not working very good here, but we were able to take our model and then serve it in an application here. And that can scale. And let's see, did I have this in the code here as well? So by default, you have to be authenticated into Union to see the app at the endpoint. But there is, I think it's just authentication. I have to look at the docs to double check. I know there's just authenticate. I should look at the docs. There's a thing you can say authentication equal to false. I think it's just that. And then you can actually share that URL out and have this as like a publicly available app, not just for you who's authenticated. Let me try one more time here with, because I had a tan background. I wonder, there's like a pillow that might work. Usually this works better, again, at my setup in home. So I wasn't prepared to try it at a different one. We saw the model was working. We just need to improve our model, basically. All right, so I know we went through a lot of stuff really fast, but if you follow along, you went through a lot and actually you train a model, but not only train a model, you put in production features like we mentioned in the talk at the beginning. We implemented caching. We didn't do local development, but basically, if you want to run this pipeline locally, you can run this really easily just by removing the remote flag. This will run it locally. So this Collab Notebook isn't set up with a GPU right now, so it might take forever, but it's, again, a way to kind of debug your pipeline without having to kick off the production jobs. So you can go seamlessly between local and production clouds. And then we have caching. We saw this. We just said cache is equal to true for tasks that we wanted to cache. For each one, we saw that resource management that we put in. Something I forgot to show is actually in the UI. If we go back to our executions, we can go look at train model. There's this view utilization button here. So we can actually see that I over-declared the amount of memory because basically the memory is all running on GPU, which we can see down here. So we actually could just do 2 GB of memory here and not allocate 8 every time. And the CPU seems like it's allocated just fine. But if we over-provision that, we can see what our compute is in production and then basically scale that to either be to bring it down or raise it up if we needed to. Type safety. So maybe it glossed over a little bit, but in all of our examples here, for all of the functions, we basically have a type that we're returning here. So when you're sharing this code or coming back to it yourself, you can kind of quickly look at these tasks and see what's expected to come in. We enforce typing on every type of object coming into. So here, like the repo ID is a string, local directory is a string, subfolder is a string, and it's returning a Flyte directory type. So we implemented all the things that we kind of talked about, plus more. Hopefully, like I was saying, this might have been kind of fast-paced. I feel like I wasn't fully on my game here at the hotel, but hopefully it was still fun. I think most people kind of stuck through. I can't see how many people actually ran everything, but hopefully some of you did. It sounded like some of you were in the chat running stuff, and if you ran everything, hopefully you had fun. And it sounds like the person who couldn't see the verification stuff, it was working now. The verify your data annotation. They also said, you said you love this feature, but I wasn't sure what or I didn't see it real time, so I'm not sure what feature you were talking about. That might have been serving. And also said, Gradio can be super helpful to share portfolios. Yeah, so Gradio, and also Streamlit is also another really good library that you can also take a look at. And you can run Streamlit apps or Gradio or really anything you want inside of a Union application here. And it can even be just an API endpoint. It's really just serving. It's under the apps tab, but it's really just serving anything. Any other questions? I actually have to wrap up in a couple minutes and go to a meeting. If there's no other questions this second, but you have questions later, join the Slack channel or find me on LinkedIn and ping me questions there. And what do people think? So like I was saying, might have been a little fast paced on parts, but if you actually ran everything, you implemented a modern pipeline, trained a model, and then actually use that model in a couple different ways, running inference on an image, on a video, and then actually we deployed it pretty quickly in an app and saw how to access like your webcam in a Gradio application. So if there's no other questions, comments, I'll probably wrap up the stream here. I'll wait another minute, see if any come in. I know there's sometimes a little bit of a delay when I'm talking as well to people seeing it on their end. All right, I don't see any other questions, so I'm probably going to wrap up the stream then. Thank you everyone for coming. Again, hopefully you found this interesting. Let me know. Also, let me know what you want to see next time. If you have other examples you'd like to see outside of just object detection. Next week, I'm actually doing one for large language models, fine-tuning them. So kind of similar like we saw today, but we'll actually be using an open source large language model, fine-tuning it, and then serving it. And I feel like there's a little bit less code with that one. And so we go through a little bit more detail. All right, I'm going to end the stream. Let me know if you have any questions on LinkedIn or in the Slack channel later. I'll talk to you later.